Unit 5A will cover momentum, impulse, momentum conservation, elastic collisions, inelastic collisions, and momentum diagrams. Momentum is a kind of difficult concept to wrap your head around, much like energy. You can't quite put your finger on momentum, but in essence, the momentum is just the mass of an object times its velocity. So a very massive object with a lot of speed will have more momentum than a less massive object moving at a slower speed. Momentum is a vector, so we need to consider what direction the velocity is pointing, and that will tell us what direction our momentum is pointing. It can be positive or negative. And momentum has the units of kilograms times meter per second. There's no special unit for momentum. And now we can think about Newton's second law, which said F equals ma, but instead we can rephrase it in terms of momentum, where acceleration is a change in velocity over a change in time. If we have mass times velocity, then we can get a momentum. So a force will end up leading to a change in momentum over time. A change in momentum is called an impulse, and this is really what you end up feeling when you feel a large force over a short amount of time. The change in momentum is just found by taking a force and multiplying it by the amount of time it takes for that force to occur. And so if we think about a graph that has force plotted versus time, we can take the area under that graph, and that will tell us about the impulse or the change in momentum. This has important consequences for ideas like collisions, where you experience a force over some amount of time. But if we make that collision take a longer amount of time, then the amount of force that you will feel like less force. This has important applications in airbags in your car or in helmets for sports safety. Think about an airbag in your car. When you're initially moving at a very fast speed and you collide with something and your speed goes to 0, then we would have a change in momentum. Your velocity changed. And you would experience a very large force in that case. But if we can elongate the amount of time that it takes for that collision to take place, if we can stretch out the amount of time in which your velocity changes, then the force that ends up being felt ends up being less force. So if you were to just collide with a wall in your car and it takes a very short amount of time, you'd feel a lot of force. But when there's an airbag in your car, that kind of slows down the change in momentum so that it happens over a longer amount of time, and that causes the force that you feel to go down. We introduced another new idea of conservation. Previously we had energy conservation, and now we have momentum conservation, which says that for a closed system where there's no external forces acting on this system, that the momentum will be conserved before and after a collision. However much momentum there was in our system in the beginning will equal the amount of momentum that there is in the end. We can expand on this momentum conservation by thinking about how many objects are in our system. So if we have 2 objects in our system, we can write out the momentum of each of those objects individually in the initial and final states, and then we can multiply the mass and velocity for each of those objects in the initial and final states to set them equal to each other and state that momentum will be conserved. So in this situation where we have 2 cars bumping into each other, we can think about the momentum that they each had before the collision, and that should be equal to the momentum that they each had after the collision. In this case, the car in the back bumping into the car in the front will cause its momentum to change. Right now we're talking about collisions, and there's 2 major kinds of collisions when we're talking about momentum conservation. There are elastic collisions, which conserve both momentum and energy, and these elastic collisions occur when objects bounce off of each other. So if I have 2 blocks sliding toward each other and then they bounce off of each other, it should be true that their momentum in the beginning and the end is going to be the same. So we could carry out momentum conservation just like we did in the previous slide, but for an elastic collision, we also would have energy being conserved. There's no energy being given up to the outside environment. And that means that we could also use energy conservation to say that the kinetic energy of each object in the beginning will be equal to the kinetic energy of each object in the end. And remember, for elastic collisions to occur, there must be no external forces acting on our system. This has to be a closed system. We can contrast that with inelastic collisions, which is a collision where momentum is conserved, but energy is not conserved. we lose some of the energy to the environment. This will happen when objects stick together and they collide. Sometimes we call a collision where objects stick together perfectly an inelastic collision. And in this case, momentum will definitely still be conserved, and we would carry out the momentum conservation equation that we talked about previously. However, in an inelastic collision, some kinetic energy will end up being lost. And in that case, that means that energy will not be conserved. We cannot set the initial energy equal to the final energy in this case. So here we have two blocks that are heading toward each other, they run into each other, and then they end up sticking together. And in this case, the kinetic energy is not going to be the same in the end as it was in the beginning. Our diagrammatic model for this unit is called a momentum diagram, which is used to represent the amount of momentum in our system before and after a collision. The steps for creating a momentum diagram are as follows. First, you'll create these axes. The vertical axis will represent the velocity. So each object might have its own velocity, and we'll represent that in terms of the vertical height of these rectangles that we end up drawing. The horizontal axis will represent the mass. And so if an object is more massive, it will end up having a wider rectangle in these diagrams. And also it's important to note that we can have objects moving in the negative direction, so we need to include some negative values on this vertical axis. You need to draw it such that you could include positive values or negative values. Then you draw a rectangle for each object. This rectangle will have a height that represents the velocity of each object, and the rectangle will have a width that represents the object's mass. So the more massive an object is, the wider this rectangle needs to be, and the faster it's moving, the taller this rectangle needs to be. Then we think about the area of this rectangle, because if we have mass on the horizontal axis and velocity on the vertical axis, if we multiply those two numbers together, we would get the momentum, and that is represented by the area of this rectangle right here. And lastly, if momentum is conserved, which it always will be for any collision, the total area of both of these rectangles added together should be the same in the initial situation and the final situation. So in this scenario, I've drawn two objects that have the same mass. Their rectangles have the same width. And in the initial situation, I have one object that is moving with some velocity toward the other. It's moving in the positive direction. It's got a positive velocity. And the second object, the red object, doesn't have any velocity at first. So we have one object moving toward another one that's not moving. And they're going to bump together and then stick together as they move. So in the final situation, when they do end up sticking together, we would find through momentum conservation that they would both have the same velocity after the collision. That's why both these rectangles have the same height. And they also still both have the same mass. And now we can think about the area of both of these rectangles added together. The total area in the final situation has to equal the total area in the initial situation. And that's why when the two objects end up sticking together, they will lose some velocity, but they will both move together. And when their masses add up and we think about their individual velocities, the total area here, which represents the total momentum, should be equal to the total area here, which represents the total momentum. So that's how you create a momentum diagram. This is a way of representing momentum conservation visually. That'll cover everything for Unit 5A. I'll see you in the next one.